This presentation focuses on key aspects of helping students begin to develop multiplicative reasoning. Prior to teaching students multiplication and division, it is important to verify that they have developed the prerequisite ideas that multiplication and division build on. In order to operate on equal-sized groups of objects, students need a concept of number as an abstract composite unit. Here are a few tasks that you can use to determine if your students are ready to engage in instruction that supports multiplicative reasoning. Counting on without physical objects, through 10 strategies, and missing add-in problems, the first type with the second add-in missing and the second type with the first add-in missing. Counting on is a strategy children use to find the total number of objects in two sets. They first count the first set. For example, if there were 6 objects, they would count 1 up to 6. And then they would count the second set, say it's 5 objects, and they would count 1 up to 5. Then they would find the total by starting at the last number they said from the first set and continuing their counting sequence. So if they had counted up to 6 for the first set, they would continue their counting 7, 8, 9, 10, 11 to find the total of both sets. What we're interested in here, though, are students being able to use counting on. If students are using through 10 strategies, this is another strong indicator that they've developed an understanding of the number that would allow them to make sense of multiplicative situations. A through 10 strategy is when you're given 2 add-ins and you break up or decompose one of those strategically in order to create a combination of 10 or a multiple of 10. So for example, if we had 16 plus 9, someone who's using a through 10 strategy might think about 9 as being composed of 4 and 5 and combine 16 with 4 to get 20 and then add 5 for the total 25. It's possible that students could demonstrate through 10 strategies in the tasks for counting on. If that's the case, then you have evidence that they're able to do this and that it's a strategy that they use effectively as they're solving problems such as these. But if they're not doing that on their own, you can ask them, if you thought about 9 as 4 and 5, could that help you solve the problem? Or, given another problem, 18 plus 7, before the student starts counting on, ask them, is there a way to think about the 7 that could help you solve the problem? Missing add-in problems also can provide insight into how students are developing their concept of number. In this first example, the second add-in is missing. You have 13 colored pencils. I gave you some more. Now you have 30 colored pencils. How many colored pencils did I give you? This type of missing add-in problem tends to be a bit easier for students to solve. In the second example, the first add-in is missing. You have some jelly beans. I gave you 8 more jelly beans. Now you have 17 jelly beans. How many did you have before I gave you 8 more? So the story maybe is a little bit more complex, but what we find is that generally students have a harder time with problems where the first add-in isn't known. We're not exactly sure why, but it may have to do with how their counting sequence develops. And having the first add-in known gives them a place to start, where if we say we gave you 8 more, they may not initially think to start with 8. But either way, this is a slightly more challenging type of problem, and both of them are important to find out if students are prepared to start studying and learning multiplicative reasoning. There's a large step that students need to take when they begin to engage in multiplicative reasoning. Prior to this, students reason strictly in additive ways. Additive reasoning is sufficient for all problems students have encountered up to this point. As long as a problem concerns just one type of quantity, Additive reasoning can be used to find how many, a difference between two sets, or how many more one person has of something than another. There are lots of questions that additive reasoning is a sufficient tool to use to solve problems. On the other hand, multiplicative reasoning requires a coordination of more than one type of quantity, and we'll get into that in a little bit. Multiplicative double counting is an early form of this type of coordination. So if you think about whole number multiplication, you can conceive of it in its simplest form as a number of composite units, and we'll talk about what composite units are, but they're things that are like a number of groups, I guess you could say, and then the unit rate is how big those groups are. And together, when we multiply those, we find a product or the total number of single objects. So just a quick example, if we had 6 packs of soda and we had 4 of them, that means that 4 is the number of composite units. Each of those composite units has 6 that compose them, and together 4 times 6 would tell us how many single cans of soda we have. When I think about teaching multiplicative reasoning, I start with the assumption that students have developed number as an abstract composite unit, which again would be indicated by their ability to solve the tasks that we talked about earlier. And yet they've not developed multiplicative reasoning. So I make an assumption that this is not something that students naturally develop or should be able to make sense of immediately, but there's some learning process that has to happen in order for them to start to coordinate these different types of units. So let's talk quickly about a situation where we have 3 types of units that can be coordinated in this way. So suppose that you are making towers out of unifix cubes. Unifix cubes, if you're not familiar, are colorful interlocking cubes that can only be combined in one way. So there's only one place where you can connect these cubes together. They're distinct from multi-link cubes where you could build different types of patterns out of the cubes. These you would build towers or snakes or trains or whatever frame you want to use to talk about what a stack of these cubes might refer to. But for our purposes, we'll talk about towers that kids can make out of these cubes. And the general frame of the tasks that we'd give students is something like you have 7 towers and there are 3 cubes in each tower. How many cubes are there in all? So if you can keep those 3 bits of information in mind, it'll be very helpful as we move forward. So there's a game that we've developed that's called Please Go and Bring For Me, which is all about building towers out of cubes and starting to coordinate these different types of units or quantities. What we've found is when we start working with students with the game, it's really helpful if there's a fairly large space where they're working so that they can actually get up and walk a certain distance so that they and create towers of cubes and then bring them back. It's a very helpful place to start because of the, we think, because of the physical activity that they're actually engaging in, where they can later imagine that they are going all the way to this box and creating a tower of 3 cubes and bringing it all the way back. But anyway, in the game, there are 2 roles. So 2 students at least are playing the game together. I've also done it where there's a 3rd person who can kind of be a helper, but having 2 kids at one time is sufficient. One is a sender who's asking the other student to go and create these towers and bring them back. So that person might, so the sender might say, please bring a tower of 4 cubes, and then the person who goes and creates the tower brings it back, and the sender says again, okay, go and make me a tower of 4 cubes, and does that, say, 3 times prior to what happens next in the game. What's important, though, as you can imagine, kids playing this game, they might want to say, go and make a tower of 52 cubes and do that 15 times. So we don't really want that to happen. So we suggest that limiting the number of cubes in each tower that the sender can use, and also the number of times that they send the bringer, limit that to 2 to 9, somewhere in between 2 and 9 would be a good idea. So I've had some teachers who have created just simple cards, like index cards, where they've written the number on the cards, and then the sender will pick a card, and then that's the number that they use for how many times they'll send the bringer, or how many cubes are in each tower. It's how you structure it is totally up to you, but there are some ways to support students in the game. Building the towers is important, but even more important than that is after the bringer has created all of the towers and they're back together with the sender plays the role of asking some questions. And again, these questions could be written down and scaffolded in a way that would support the 2 kids playing. But the questions are really important. How many towers did you bring altogether? How many cubes are in each tower? How many cubes did you bring in all? And how did you find the total? These questions, even though they may seem to be painfully obvious because the one student went to get the towers and put the cubes in the towers and brought them all back, what's important is these questions help the student develop these different units as quantities. So the towers, the number of towers becomes a quantity. The number of cubes in each tower becomes a quantity. And the total number of cubes is a quantity itself. So what's crucial is that in this one task, in this one activity, you have these 3 distinct units or quantities that the students are starting to coordinate. And they're doing it at the most basic sort of level, which is just becoming aware of them and naming them. But it's important that they're starting to associate a number to how many towers, and a different number to how many cubes are in each of those towers, and a different number to how many total cubes are there altogether. By combining these and coordinating these different units, they're starting to create a multiplicative structure that they'll be able to abstract from as we move forward with the instruction. So playing this game where kids are actually getting up and moving and walking around, we think is very important as the introductory step, but we also recognize that this could go on for too long, and it becomes at some point unnecessary to have the students walking around the room or the playground or the cafeteria or wherever you happen to find space. So after a few turns of doing the physical walking and building the towers, the game can change to just creating towers at a shared in a shared space. So if the students maybe have two desks pushed together, the sender still asks the bringer to create towers, but the cubes are already at the table, and they just build towers without the walking business. So here the sender is saying, okay, make me a tower, or go and bring me a tower of 4 cubes. And they do that repeatedly to a point, and then they go through the same exact questions that we just talked about. And then once you feel that the activity with the cubes is pretty routine, then as the teacher you can create some constraints that start to limit the student's capacity to count single cubes. So for example, if students are trying to find the total consistently by counting single cubes, you might cover the cubes, cover the towers, and even write on a piece of paper how many towers there are and how many cubes are in each tower to remind them. But the goal is to start to get them to start operating on the fact that they created towers of 4. So if I had 4 in the first one, then so far I have 4 cubes with the first tower. In the second tower, how many do I have? Some students will start to say, well, that's 8, because they either have been engaging in skip counting or because in their additive experiences they've learned that 4 and another 4 is 8, and maybe another 4 is 12. Other students might have to, starting with 4, and say 5, 6, 7, 8. That's perfectly fine, and continuing on by counting by ones. But the crucial thing to pay attention to if you're the teacher is, are they counting by 4 at a time? So are they saying, all right, I have 4, that's in the first tower, and then I have 5, 6, 7, 8, that's the second tower, 9, 10, 11, 12, that's the third tower. So they may not be able to operate with a 4 as a single quantity to add on to what they had before, but they can keep track of how many I have altogether as I'm going by adding 4 at a time. So even though I'm doing it singly, I am showing you that I know that this tower is made of 4 as well, and I'm stopping my count at 8 and then 12 and maybe 16 because I know that there are 4 single cubes in each tower. What we start to notice as an intermediate step that many students go through, which is a really important developmental progression, is they start to use their fingers to represent a tower, and then they might count on, literally pointing on their fingers to accrue the next set of 4 or the next set of however many are in a tower. But that allows them to keep track of the number of composite units or towers and figure out how many total cubes they have altogether as they're going. Eventually, it's important to provide tasks where students are no longer using physical cubes. One way to do this is to have the bringer, instead of building towers out of cubes, to pretend that they have built towers out of cubes, and then answer the questions that follow the task. One way to support students is to encourage them to draw diagrams that would represent the towers that they pretend to make. When students first start using diagrams that are meant to depict the towers that they pretended to create, they almost always will draw diagrams with each cube represented in each tower. One of the things that we have found to be important is to encourage students, once they're able, and once you think they're comfortable with, they could do that all day and have no problem, then encourage them to draw towers that don't have all of the cubes represented in the tower physically, and instead, so if we're making towers of 5, instead of having 5 individual cubes in the tower, have them draw an empty tower, like the outline of a tower, and write the numeral 5 to represent how many cubes that tower has. This helps students to move from the more concrete to the more abstract. Eventually we need students to be able to operate with quantities that are represented by numerals, and to understand the connection between the numerals and the quantities that they represent. We suggest that this is a good time to introduce the symbolic equation that we use for multiplication. You can introduce the symbol x as meaning the number of times that we brought a tower of a certain size. When we do this, we find that students make a really strong link between the symbolic representation of the situation and their understanding of what's happening in the story. And we find that this has been extremely powerful to help students find the answer to these stories. And then there's a very strong link between their experience of creating towers and finding how many towers they brought, finding how big the towers are, and finding the total number of cubes is really important. This is also a great time to introduce academic language to the students. It's once they have a conceptual basis for needing the vocabulary, then talking about factors and multiples and products is a really good idea. Prior to this, these terms may not have much meaning, and then it becomes, I wonder if it's a game of, can I remember what this thing is called, as opposed to, I have an idea and this word goes with that idea. So we think that this is a good time to introduce vocabulary that then will facilitate communication with other students and within the class about what you're working on. So as we continue thinking about how students can develop meaning for multiplication and division, we're looking now ahead to how multiplication and division are related. They are inverse operations, so if you think about one kind of division, quotative or measurement division, you're given how big the towers are, or the unit rate, and you're given the product, or the total number of single cubes. And what you're trying to find out is how many towers would I have if they're all this size and I have a total of this many cubes. Whereas in partitive or sharing division, you're not given how big the towers are, but what you do know is how many towers there are, or the number of composite units, and you know the total number of single cubes. And you're trying to find, if I have this many towers and I have this many cubes, then how big would the towers have to be in order for that to work? So again, the situation of please go bring me, or the context, can give students a foundation to start to make sense of these quantities that are related to each other, and different ways that they can be coordinated. I feel pretty strongly that this is a powerful way to teach multiplication and division, where kids do not need to start with the facts. They don't need to know what 4 times 5 is in order to engage in reasoning this way, but they do need some careful and thoughtful sequences of tasks that can help them build these complex relationships, so that their thinking is more powerful. So if you imagine working with students, and you're working on one of the kinds of division, you can ask students to imagine that we've already played Please Go and Bring Me. And the goal is can you find the number of towers if you're given the total number of cubes and how many cubes are in each tower. So if you're given the unit rate and you're given the total, can you find how many composite units you'd have to have, or the number of towers that you would have to have? But it gives students a way of starting to go back to an experience that they've had that they can abstract from, that they can reflect on and try to make sense of at a different level. Or if we're given the total and the number of composite units, the number of towers, then can you find the unit rate? Imagine we played Please Go and Bring Me. Can you find how many cubes are in each tower if you know the total number of cubes and how many towers there are? So I just want to make a comment that that using multiple contexts is important. What I've been talking about so far is using a single context to build a pretty robust concept. And my thinking with this is if students have an anchor or a foundational type of activity that they can relate to, then when they're thinking about other story problems or other situations that maybe don't have a context, they don't have a story that's the primary focus, that they can go back to this game and they can think with it. They can take themselves back. So if they're given a problem like 12 times 10, they can actually think about, well, what if I made 12 towers and they each had 10 in them? Could I figure out how many total cubes I have? So it gives them a way to think about and translate things that maybe are a bit more abstract or without a context, and provide a context from their own experience that would help them make sense of this new situation. A little bit about how this sequence of lessons works and what assumptions I make when I think about how to teach somebody something that's pretty complex, that many kids have a hard time understanding. It starts with knowing that they have what they need in order to make sense of the new material. This doesn't mean that they've mastered everything comes before the time that multiplicative reasoning is introduced or multiplication and division are introduced. What it does mean is knowing the kinds of concepts that students need to be able to build on in order to make sense of multiplication. So it's all about having number, having an understanding of number that's robust enough that they can actually operate on quantities that are bigger than 1. So if I have an understanding of 5 that allows me to think about a bunch of 5s, then I can start to think about multiplication. But if I can't think about 5 that way, then having a bunch of 5s isn't going to be very useful. I'm not going to be able to make much meaning from that. So this is crucial. Thinking about what the student's goal-directed activity is and how to scaffold it. I think this sequence of tasks or lessons I think is a good example of a way to think about scaffolding students' progression in their thinking from an additive world to one that involves coordinating different quantities in a multiplicative way. So the tasks and the questions themselves are helping students to start to develop a goal or an anticipation of, okay, I'm going to build some towers. They're all going to be the same size. Then I'm going to have to find out how many cubes there are altogether, and I can find out based on how many towers I made and how big those towers are. And then as they're thinking about the anticipated result of their activity, right, they take the number of towers and the size of the towers, and they can find the number of cubes. As they do that and start coordinating these different quantities, they can start to notice that when I built 4 towers of 5 and I got 20 cubes, and I built 3 towers of 6 and I got 18 cubes, that what's common across these things is I have some number of towers that are all the same size, and I wind up finding how many cubes there are, and so they can start to anticipate what the result of their activity might be, and then they have a way of making sense of that. So what's happening, I think, is they're starting to notice commonalities across their experiences, and together over time and over these experiences and reflection, they can start to develop new ideas. And in this case, it's the coordination between these different quantities. Another thing that I emphasized here is the importance of going from maybe what we might call less symbolic to more symbolic, or less abstract to more abstract. We started with cubes and counting the cubes and finding out how many there are altogether given these towers, to how do kids start to think about equations that involve multiplication, and how does it build through the figural or pictorial representations to the symbolic representations. Bruner talks about a different sequence of ways of interacting with the content, but he thinks of it as enacted to iconic to symbolic. Both of those, I think, are equivalent ways of thinking about what's happening, but in either case, having students start to represent the more physical objects to starting to pretend that they're engaging with the physical objects to the point where they don't need to pretend anymore, that they can just work on situations that involve numbers and symbols. That's what we're trying to get to. How we get there, I think, is what's important. How do we help students develop facts, multiplication facts in particular? What I can say that I've learned is when students are given a way to think about situations that involve multiplication, like what I've described here, and they start to develop a cognitive structure of what multiplication is about, then you can start to, I think, meaningfully help kids develop more proficiency and fluency with multiplication facts. One student that I've worked with who was a beginning 5th grader and was about 3 grade levels behind many of his peers, was being asked to memorize his multiplication facts, and you can imagine was struggling with that. So once he started playing this game and we started helping him develop some structure to the quantities that he's engaging with, he very rapidly gained a way of thinking about multiplication facts and that they had meaning, because he could think about it in terms of towers and cubes and things like that. And then the other important thing was he started to get some facts, and then once he had those, he could figure out other facts that were somehow related. So if he knew 5 times 5, for example, was 25, and he could think about that as, well, that's 5 towers with 5 in each tower, and I know that's 25, that's something I know, then he could figure out, well, what if I had 7 towers with 5 in each tower? And it just was kind of magical. It wasn't magical, but it was pretty remarkable how quickly he was able to make sense of, oh, that's just 2 more towers with 5 in each, which is 10, so it's 35. And once he was able to do that, then I had him practice in a pretty structured way, where he wrote out the multiplication facts, the table, but he actually wrote it out, didn't fill in empty boxes, but wrote, the 4 times 1 equals 4, 4 times 2 equals 8, and so on. But once he showed me that he knew some of the facts, then we just focused on the ones that he didn't know already, and that became really effective practice, because it boiled down to maybe 6 or 7 facts that he didn't really know, and so we worked on those from this towers and cubes perspective. But once we narrowed it down to the ones that he really needed to work on, the work became so much easier and less frustrating for him. And by the end of, I think, 15 times of working with him for about an hour each time, he was just about back on grade level. So it's a sensible way, from my perspective, to build students' capacity to be more fluent with their facts if we start with a conceptual basis for the relationships that we're asking kids to really understand. The facts come, for me, after the understanding of the structures and the relationships. So after this presentation, if you could move ahead with the next activity, there I'm asking you to create a lesson plan that you think would support students' development of multiplicative reasoning. The closer it can be to where your students are right now, the better. So try to figure out, are there some students who are ready to start engaging in multiplicative reasoning, but as yet haven't shown that they're doing that on their own, or through what you've been doing with them. And I'd encourage you to try the game and use the structures that are in this presentation to support students getting to where they need to go. If you have students who are starting to work on division, but they're seeming to not maybe make much connection to what they learned with multiplication, then you might have them do some building of towers and then talk about that situation from a different perspective, from a division perspective, where they know the total and they know either the number of towers or the number in each tower, and go from there. Anyway, I look forward to seeing what you come up with your lesson plan, and later see some artifacts that the students create.